Consider a carbon chain in which one terminal carbon atom is joined to a chlorine atom C3, C2, C1, Cl. Chlorine has a greater electronegativity than carbon. Therefore, the electron pair forming the covalent bond between the chlorine atom and C1 will be displaced towards the chlorine atom, negative, then positive. Vacancy in C1 due to the attachment of the chlorine atom, which has a greater electronegativity than the carbon atom, which gives the del negative, the electron density in chlorine is greater than the carbon atom C1. This causes the chlorine atom to acquire a small negative charge, del negative, and C1 a small positive charge, del positive. Since C1 is positively charged, it will attract towards itself the electron pair forming the covalent bond between C1 and C2. This will cause C2 to acquire a small positive charge, del plus, but the charge will be smaller than that of C1 because the effect of chlorine atom has been transmitted through C2 to C1, through C1 to C2. So del positive is less than del positive. Similarly, C3 acquires a positive charge, del positive, which will be smaller than on C2. This type of electron displacement along a chain is known as the inductive effect. The inductive effect, where the electron density is moving towards the chlorine atom. This is showing a minus I effect, that is the inductive effect, and a plus I effect on the C1 with respect to chlorine. It is permanent and decreases rapidly as the distance from the source increases. So as the distance increases, the effect also decreases. From the practical point of view, it may be ignored after the second carbon atom. So after the second carbon atom, this effect can be ignored. It is important to note that the electron pairs, although permanently displaced, remain on the same valency shells. So electrons are not moving anywhere, just the charge density is different in each atom. Inductive effect may be due to atoms or groups and the following in the order of decreasing inductive effects. So this is the decreasing inductive effect of plus I. We have O negative, CO2 negative, the decreasing plus I effect, CH3, CH2, 2, CH, CH3, CH2, and CH3 at last. So out here, out so out here, due to the bulkiness of the atoms of the compound CH3, as you can see here, this is similar to this. and the energy, the dissociation energy, is the least compared to the rest. This is decreasing as the bulkiness is decreasing. So we have here the plus I effect. This is due to the plus I effect. The dissociation energy of the bond dissociation energy of this compound is less than this compound. That is this, due to the plus I effect on the carbon atom, carbon and hydrogen atom. We have to look with respect to the hydrogen atom from this point of view. For measurement of relative effect, inductive effects, hydrogen is chosen as reference in the molecule. Say for example, Cr3H, hydrogen is the reference medium as a standard. If when the H atom in this molecule is replaced by Z, say replaced by Z after some reaction, Z can be any atom or group, the electron density in the Cr3 part of the molecule is less in this part than in Cr3H. So electron density del plus is del del plus, and this is del plus. This energy, the electron density in this carbon atom attached to the H is than greater than the carbon atom attached to Z, any compound Z, any group or any atom. Then Z is said to have sorry, Z is said to have a minus I effect. So a minus I effect due to the electron attracting, it can be said minus I effect can be also referred to as electron attracting, getting a del negative of electron density. Due to this, the charge density in this compound, the carbon atom of this compound is less than in this due to the H atom. Electron attracting or electron withdrawing, the minus I effect. If the electron density in the Cr3 part is greater than Cr3H, then Z is said to have a plus I effect, electron repelling or electron releasing. For example, Br, bromine, is minus I, and C2H5 to H5 is plus I, the carbon. We're focusing on the carbon here. This terminology is due to Ingold, 1926. The theory of mesomerism was developed on chemical grounds. It was found that no structure formula could satisfactorily explain all the properties of certain compounds. Example, benzene. This led to the idea that such compounds exist in a state which is most combination of two or more electronic structures, all of which seem equally capable of describing most of the properties of the compound, but none of describing all the properties. Ingold, 1933, called this phenomenon mesomerism, that is, an intermediate structure between the parts, an intermediate structure. This is the resonance hybrid or the mesomerism hybrid. Heisenberg, 1926, from quantum mechanics, supplied a theoretical background for Mesomerism. He called it resonance. And this is the name which is widely used. The chief conditions for resonance are the positions of the nuclei in each structure must be of the same or nearly the same. So the structure of the nuclei is same in all the resonating structures. The position of the nuclei in such structures. Second, the number of unpaired electrons in each structure must be the same. So the number of unpaired electrons must be same. Say for any atom, number of unpaired electrons is 3. So in every resonating structure, the unpaired electrons must be 3. This is just an example. Each structure must have about the same internal energy. That is, the various structures have approximately the same stability, which gives us the resonance hybrid, which shows the cumulative energy, the internal energy of all the resonating structures. It is shown by this small dots. As a cation, as the cation or the anion travels throughout the benzene ring. This we get this. In in a resonance hybrid, all the molecules are the same. A resonance hybrid cannot be expressed by any single structure. The difference between the enthalpy of formation of the actual compound, that is the observed value, and that of the resonating structure, which has the lowest internal energy obtained by calculation, is called the resonance energy. Thus, the value of resonance energy of any resonance hybrid is not an absolute value. It is a relative value, the resonating structure containing the least internal energy being chosen as the arbitrary standard for the resonance hybrid. The greater the resonance energy, the greater is the stabilization. So greater the resonance energy, the greater the stabilization. The resonance energy is a maximum when the resonating structures have equal energy content. And the more resonating structures there are, the greater is the resonance energy, provided that all contributing structures have similar stabilities. Another property of the resonance hybrid, which differs from that of the resonating structures, is the bond length. That is the equilibrium distance between atoms joined by a covalent bond. The normal length of the carbonyl double bond in ketones is about 1.20 angstrom. In a resonance hybrid, the electronic arrangement and bond lengths will be different from those of the resonating structures. Consequently, the observed dipole moment may differ from that calculated for any structure. So the dipole moment mu E times D may differ from that calculated for any structure, for any one resonating structure. The larger the number of halogen atoms on the alpha carbon atom, for this, X being the halogen, this being the alpha carbon, this is a compound. Sorry. For this compound, we have the inductive effect minus I on the halogen groups and plus I on the alpha carbon. The larger the number of halogen atoms on the alpha carbon, the stronger is the inductive effect, and consequently, the stronger is the acid. Also, the further removed the halogen atom is from the carboxyl group, the weaker is the inductive effect at the carboxyl group, and consequently, the weaker is the acid. In the same way, since an alkyl group is electron repelling, increasing their number on alpha carbon atom should decrease the strength of the acid, since release of the proton will be hindered. Since minus I groups in the alpha position, example X NO2 OH, increase the strength of the acid, and the plus I groups, methane methane, weakens the acid. The measure the measurement of the pKa is of the various substituted acetic acids affords a means of measuring the relative inductive effects of different groups. So the measurement of pKa's of various substituted acetic acids affords a means of measuring the relative inductance of different groups.